Welcome again to my YouTube and Facebook channel. In the previous video, our topic was stability of carbocations. Now today I will be concluding this topic, video number 3 on this topic. Again I have written stability of carbocations. First, a reminder, carbocations are stabilized when they are attached to electron donating groups which show positive inductive effect or which show positive mesomeric effect. And carbocations become unstable when positively charged carbon is directly attached to electron withdrawing group which show negative inductive effect or negative mesomeric effect. So plus I and plus M make the carbocation stable, and minus I and minus M effects make the carbocations unstable. Let us start one more part of that. I have written here some carbocations in order of their decreasing stability. You can see the most stable carbocation is this. It is called cyclopropyl methyl carbocation. It is the most stable carbocation among all these. Why so? I will tell you later on, because of that concept is called a dancing resonance. I will tell you at the end of this video what is meant by dancing resonance. Why this carbocation, even though it is not attached to the double bond, why it is most stable carbocation? You can see number 1 here, top, most stable among these. Then followed by this carbocation, it is called triphenyl methyl carbocation. You can see this positively charged carbon, it is stabilized by pi bonds of 3 rings. I mean, these pi bonds will interact with this positive charge, and pi bonds of 3 rings will interact with this positive charge. So more the number of rings directly attached to the positively charged carbon, more will be the number of resonance structures. That carbocation becomes more stable. Followed by this carbocation, this positively charged carbon is attached to 2 phenyl rings. So this positive charge interacts with pi bonds of 2 rings through conjugation. It will also be a more stable carbocation, but less than this triphenyl methyl carbocation. After this we have this one, tertiary carbocation. You know, methyl groups exert hyperconjugation. I have told you, in methyl group, sigma bonds of methyl group interact with empty orbital of carbon and stabilize the positive charge. So this tertiary carbocation will be more stable. Then after tertiary carbocation we have this one, benzyl carbocation. This carbon having positive charge is attached to only 1 phenyl ring. It will also be stabilized through resonance, through conjugation. So after this we have allyl, CH2 double bond CH, then CH2 positive charge. This positive charge will also interact with this pi bond. It is called allyl carbon. Allyl carbon contains positive charge. It will also be more stable. Then after this we have this 2-degree carbocation. Carbon carrying positive charge attached to 2 methyl groups. It will be stabilized through hyperconjugation. Then after 2-degree carbocation we have got this 1 degree. 1 degree carbocation, positively charged carbon attached to only one methyl group. So this is the order of stability of some carbocations. Remember, stability through interaction with pi bond is more than the stability through hyperconjugation. I am repeating, stability of carbocation through its interaction with pi bond is more than its stability through hyperconjugation. So that's why triphenyl methyl carbocation is more stable than diphenyl methyl carbocation. I hope you are getting my point. So this is the decreasing order of their stability. Now the question is, you can ask, sir, why this one? How it is more stable? Even though this carbon has no adjacent double bond, there is no electron donating group, why it is more stable carbocation? Of all the carbocations, it becomes the most stable. Let's find. The question is, why is cyclopropyl methyl carbocation most stable? What is the reason for its greater stability? So I will draw a structure like this. This is cyclopropane and this is this one. It is the most stable carbocation, even more stable than triphenyl methyl carbocation or tertiary carbocations. The reason is because of dancing resonance. What is dancing resonance? I will tell you. In cyclopropane, carbon, 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 this bond angle is only 60 degree. 60-degree bond angle causes maximum angle strain, which makes cyclopropane ring highly stable. So the result is the ring tries to open up. It's a closed chain of 3 carbons. You can see carbon, carbon, carbon. In order to minimize angle strain, which causes maximum repulsion between bond pair and bond pair, so the ring tries to open up. That is called dancing resonance. But in dancing resonance, pi bonds do not participate. Sigma bonds participate. You can see like this. This bond will break like this. So this carbon and this carbon will be joined and this bond will form a double bond. So we will get this structure. Here we will get a positive charge on this carbon. So ring opens up, or we can have structure like this. CH2 here we will get positive charge. So this opening of ring, movement of sigma bonds of cyclopropane, why they open up? In order to avoid, in order to minimize the repulsion. That is called angle strain. So this sigma bond neutralizes this positive charge, making the carbocation more stable. This effect we call dancing resonance. Dancing resonance. In this type of resonance, only sigma electrons, sigma bonds of cyclopropane ring participate. It is different from normal resonance in which pi bonds participate, lone pairs participate. I hope you got it. This sigma bond joins this carbon and this carbon. And this sigma bond forms a double bond. Positive charge comes over here. In another structure, positive charge will come on this carbon. This dispersal of positive charge helps in stabilization. That is why cyclopropyl methyl carbocations become more stable, even more stable than triphenyl methyl carbocation, where pi bonds are responsible for stability. So I will write here. You can see carbon carrying positive charge is attached to 3 cyclopropane rings. It will be more stable than this, while we have only 2 rings, cyclopropane rings. And this one will be more stable than this structure. Reason is, as I told you, dancing resonance. So these types of carbocations become more stable than those where stability comes through interaction with pi bond or through hyperconjugation. That's why while arranging the carbocations, I kept this one at the top in stability. Okay, now one question. One question. Which of the following carbocations, which of the following carbocations is the least stable? Least stable, not most but least stable. I will write 4 options. Option B, then option C is then option number D is this one. So these are the 4 options, and we have to answer, we have to tick mark that carbocation which is the least stable. You can see option number C, OH, it shows plus M effect. It makes carbocation more stable because of lone pair on oxygen. CH3 group, it shows hyperconjugation. Hyperconjugation also stabilizes carbocation. You can see option number A, nitro group. It shows strong minus M effect. So when there is strong minus M, carbocation becomes unstable, because this nitro group will remove pi bonds from the ring. It will increase positive charge at carbon. So option A is correct. Thank you for today for watching this video, and do subscribe to this channel for more videos, and let me know your opinion, your suggestions by writing in the comment box.